Hello, welcome to another video of Dr. Viv on graduate classical mechanics. Today we shall take a look at the important equations known as Euler equations, discuss the notion of spin stabilization, the precession of a heavy top, and as a fun problem, we shall estimate how much the North Pole has wandered since the impact that caused the extinction of the dinosaurs. So when I say spin stabilization, I mean something like this. Everybody knows that a frisbee or a hat needs to be spun in order for it to travel. So you need to spin it like this. And that stabilizes the motion. This stabilization also involves wobbling. So if you look at this frisbee carefully, it's going to wobble as it spins. We'll be studying that wobble and show that the wobble is actually stable. And that's what leads to stabilization due to spin. The notion of precession has to do with symmetric top like this one. Any top that has one axis of symmetry is known as a symmetric top. This top has got another axis of symmetry, which is this one. And any two perpendicular axes also are symmetric, but you don't need that. This is a symmetric top. Now this does not display precession because the axis where it's touching the paper is allowed to, the point of contact is allowed to move. But if I fix the point of contact like I'm about to for this gyroscope, then this is a gyroscope manufactured by the Tedco company. It's a very nice device. I have put some twine around it. So let me gun the gyroscope. So it's moving quite fast. And if I keep one axis fixed, you will notice that as time progresses, that axis tends to rotate. So right now this axis is rotating at a certain angular speed. The actual angular speed of the gyroscope is very high, several RPM, but the rate of rotation of this axis is not very high. But as the gyroscope slows down, you notice that this rate becomes higher and higher. So that's one of the characteristics of this precession motion, and we wish to study that. So gyroscopes are very useful because they tend to maintain a fixed direction, and they are used in all kinds of navigational compasses ranging from ships, like the ship Titanic had a gigantic gyroscope that was several hundreds of feet long, and airplanes have big gyroscopes to maintain the cruise control, and of course satellites in orbit have big gyroscopes too. Now the last problem is a interesting application of Euler equations, and that has to do with what happens when you have a body that has been spinning steadily for some time and then something comes and hits it. This is the fate of every planet in our solar system, right from the days of early bombardment from planetesimals and big meteorites. And then the most recent example in our recent history is the great extinction that is suspected to have killed off all the dinosaurs 65 million years ago. I said it might have because there are competing theories that place more emphasis on volcanism or volcanic activity in the Deccan Traps in southern India. Anyway, let's now get to the tasks at hand, starting with Euler equations. So Euler, when you diagonalize the moment of inertia tensor, let's say you have found, in the previous video I show you how to do this, say you found a basis in which you can diagonalize the 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 moment of inertia tensor. So in that basis, you can write Newton's second law from point of view of the frame S prime. So in frame S prime, I'm going to write Newton's second law, and Newton's second law is written like this: the sum of all the external torques, which I'll just write as gamma prime external. Gamma is the symbol for torques, is the rate of change of angular momentum dl prime by dt. Now, because of the d by dt in the prime frame, the d by dt operator in the prime frame is equal to the d by dt operator in the unprimed frame S plus omega cross. In this case, it's omega cross L. So that is the usual d by dt in the prime versus unprimed relation. But these equations were first written by Euler, and so these are called Euler's equations. Now, I'm just going to write gamma prime x as simply gamma so that I don't have to worry about writing the subscripts each time. So gamma is dl by dt. Well, in the body frame, dl by dt is just the moment of inertia tensor written as a dyad. I won't be doing this very often, times omega, the rate of change of omega dot, okay, because of the d by dt. L by itself is I omega, but d by dt is this. Well, here I'm making an assumption. I'm making the assumption that the moment of inertia doesn't change with time. If it does, then you have another term that involves I dot. So let me just write what the general case would be. I dot omega plus omega cross L. So this will be the full expansion of this in the most general situation where even imagine bits and pieces of this top are flying off or evaporating if it's made of ice. So that would be described by those equations. Now, this generally doesn't happen for the most part. Even for Earth, it actually happens. Every day, the Earth collects 400 tons of debris from outer space. But if you ignore these things, then that term goes to zero. Because compared to the moment of inertia of the Earth, this rate of change of moment of inertia is extremely small. So now we have a simplified set of equations. Let's write it in the form of matrices. So I'll write this as gamma 1, gamma 2, gamma 3, where gamma 1, gamma 2, and gamma 3 are the components of the torque in the frame S prime along the x, y, and z axes. And that is equal to I dot omega, but because I is a diagonal basis, we just have three terms, and that is lambda 1, omega 1 dot, lambda 2, omega 2 dot, lambda 3, omega 3 dot, plus the cross product can be written as the following. It's I hat, j hat, k hat. Well, to be frank, I have to write as a determinant. I hat, j hat, k hat, omega 1, omega 2, omega 3, L1, L2, L3, which are lambda 1, omega 1, lambda 2, omega 2, lambda 3, omega 3. These brackets are just fun brackets. They don't mean anything. But now let's write this one more step. I'll repeat what I wrote here. And then I'll expand the determinant and write the determinant as another column vector. So this time the round brackets are legitimate. So this gives me negative lambda 2 minus lambda 3, because I hat component is omega 2 lambda 3 minus omega 3 lambda 2. And the j hat component is going to be, I'm going to write it as even though this is omega 3 minus omega 2, I'm writing it as negative omega 2 minus omega 3. J hat component already comes with a negative sign. So I'm just put this thing to guide me. That's a plus, that's a minus, that's a plus. So this I hat component was lambda 3 minus lambda 2, but I'm writing it as negative lambda 2 minus lambda 3. And the lambda, the second component is going to be with a negative sign already, so that I won't try to mess with. That's going to be lambda 3 minus lambda 1. Omega 3, omega 1. And the last term will come with a positive sign, so I will mess with that. That's without messing, it would be lambda 2 minus lambda 1, but with messing, it will be lambda 1 minus lambda 2. Omega 1, omega 2. So the reason I wrote it like this is because it answers to the symmetry of the magic circle. So you can use the magic circle to remember this version of Euler equations. So 1 comes with 1 here, and then 2, 3. 2 comes with 2 here, and then 3, 1. And then 3 comes with 3 here, and then 1, 2. So the minus sign enables you to have that symmetry. So that's Euler's equations written out in full detail. Now to use these equations to address these various problems is our next ambition. So what we're going to first do is do a simple example where lambda 1 and lambda 2 are equal to each other, and then lambda 3 is the one that varies. So let me this addresses all precession objects like tops or the Earth. So that's the first application. I think there's a figure to go with this. That's the figure. Now there's a lambda 3 associated to the axis E3, and this is rotating about the E3 axis with some angular velocity omega 3. And the application we have here is that it's a symmetric top. Which means lambda 1 is equal to lambda 2 equals lambda, and lambda 3 is different. So we'll keep lambda 3 as lambda 3. All right. When you do that, immediately you notice, because lambda 1 is the same as lambda 2, the third equation becomes very simplified. So let's go with the third equation first. I get there's no external torque in the third direction, because any torque that would exist would be, so a torque, what is torque in this case? It's going to be gravitational in nature. So that's going to be your mg. That comes like this. If you think about what the meaning of torque is, it is this distance r cross mg. Now, I invite you to use your right hand to show that r cross mg is going to be entirely in the xy plane. Because r cross mg is in the xy plane, there is no component of the torque in the z direction. So we'll write that here. R cross mg, g as a vector, is in the x prime, y prime plane. So you only have torques components gamma 1 and gamma 2. And gamma 3 is 0. Let's use that in the third Euler equation. So I'm going to get the following simplification. I'll call this Euler equation 1, 2, and 3, where 1 would be that, 2 would be this, and 3 would be that. So Euler equation 3 gives me, I'll write down what Euler equation 3 is first. Now, if you put lambda 1 equal to lambda 2, that term disappears, and gamma 3 is 0. So I get 0 equals lambda 3 times omega 3 dot. Well, that's very important. That's an important equation because it tells me that omega 3 is a constant. So Euler must have been very pleased to discover this because it tells you that the duration of the day will not change. The Earth will keep having a 24-hour day. It's not strictly true, but you can see there's no real intrinsic reason for the Earth to slow down. And, real tops do slow down. This process of the spin doesn't last very long because of air resistance and viscosity of the air, which causes a viscous drag and slows down the rotation. Eventually, this top will succumb to some sort of asymmetry and choose one direction to fall, and it'll stop spinning and fall altogether. But in the ideal situation with no air resistance, no sources of friction or energy loss, omega 3 is indeed constant. Let's see now what the other two equations give us. The other two equations, I'll write Euler equation 1 now, is gamma 1 equals lambda, because lambda 1 is just lambda, or lambda 1 and lambda 2 are both lambda. So that's just lambda times omega 1 dot minus lambda minus lambda 3 omega 2. And then because omega 3 is constant, I'll write omega 3 as omega 3 0. So that actually just as omega 0. I don't want to keep writing 3. So that's going to give me omega 2 omega 0. And then gamma 2 will be lambda omega 2 dot from this minus lambda 3 minus lambda omega 3 omega 1. But omega 3 is again omega naught. So I'll substitute for omega naught like that. Now I'm going to differentiate the first equation. If I differentiate the first equation, I'm going to get the rate of change of torque. Now, think about that. The torque involves R cross mg. Now, in the examples I showed you, the top does slowly tilt, but in robust examples like the Earth, the tilt never changes. It's 23.5 degrees for millions of years. So R cross mg will not really change with time that much. So I can think of it as approximately 0. So the rate of change of the torque itself is approximately 0. And that's going to be lambda times omega 1 double dot. So I'm differentiating the first equation. Minus lambda 3 omega 2 dot omega naught. And here, because this is constant, it doesn't get differentiated. Now, once again, if your lambdas change with time, you're going to get additional terms and more complications, but we don't have that problem. So now what we're going to do here is I'm going to use equation 2. So let me write equation 2 next. Equation 2 is right there. So I'm going to substitute for there's omega 2 dot. I'm going to use equation 2 for omega 2 dot. Use equation 2 here. So let me write down omega 2 dot from equation 2 first. Omega 2 dot is going to be gamma 2 divided by lambda. And then I'm moving everything to the other side and dividing by lambda again. So I get a plus lambda 3 minus lambda divided by lambda times omega naught omega 1. That's omega 2 from equation 2. So that I'm going to use in there. So let's see what I get. I get 0 equals lambda omega 1 double dot minus lambda 3. I'll take the omega naught. And then omega 2, which will be all of this. Gamma 2 over lambda plus lambda 3 minus lambda over lambda omega naught omega 1. So that's a handful. But this is good because it looks like a good second order differential equation with no cross terms. This here, you had omega 1 and omega 2 related. So all these cross relationships vanish now. So let me write one more equation. And what I can do is divide throughout by lambda. So I get 0 equals omega 1 double dot minus lambda 3 over lambda times omega naught. And then here, I'll multiply each term, gamma 2, and over here, I'll write this as, that's lambda 3 minus lambda with a negative sign, lambda minus lambda 3 with a negative sign. I'll absorb the negative sign and make it lambda 3 minus lambda. Then it's going to become that squared, especially after I divide by lambda. There's already a lambda there. So I'll get plus lambda minus lambda 3 over lambda times omega naught, that whole thing squared times omega 1. So that itself is a really interesting equation. Let's see what that tells us. Now, in most examples, the external torque is really small. So for examples like throwing a frisbee in the air, or any example, frisbees are usually thrown in the horizontal fashion. So as long as the frisbee is not thrown at a steep angle or something, you can think of gamma 2 as approximately 0. So we're trying to get some result out of this. So gamma 2 is approximately 0. That means the middle term goes away. And then the other way of thinking about this is lambda, there's a lambda squared here. So another way to think about this, if you don't want to say that the gamma 2 is 0, another way to think about it is saying that lambda minus lambda 3 over lambda squared could approximately be equal to 0, because the square of a principal moment is definitely bigger than the principal moment itself. So you can think of this as approximately 0. Either way, the product of these two things is definitely close to 0. All that is justification for throwing out the middle term. Well, then what do I get? I get 0 equals omega 1 double dot plus a quantity I'm going to call omega body squared times omega 1, where omega body squared is everything I have not written, which is lambda minus lambda 3 over lambda times omega naught squared. This is the body precessional speed, omega b. So we'll write down what omega b is. It's the absolute value of lambda minus lambda 3 over lambda times omega naught. It's a very important quantity, and it's used to make various estimates of rotating bodies. Now, more importantly, what this system of equations shows us, when I say system, we play the same game. So likewise, if you differentiate, in other words, what is playing the same game? Differentiate equation 2 first, then use equation 1 to substitute for omega 1 dot, and then repeat the same process. You're going to get the same equation, with the only difference being that you're going to get omega 2 double dot plus omega b squared omega 2. So what this shows is that omega 1 and omega 2 simply oscillate simple harmonically. If you think about this frisbee, it's just going to do this. It's going to oscillate back and forth with an angular frequency of omega b, both along this axis and along that axis. So that is what these equations show. So this is the concept of spin stabilization. If you want to retain a cool persona, when you come into if you see an old Western movie, when the fellow walks into a bar, they throw their hat. They don't throw it like this. They throw it with a spin, because then the hat would spin elegantly and land on the hat rack. If you're good enough, you can do that. So you always use a spin to stabilize your rotary motion. All right, now we have finished our second task, the spin stabilization. Now we have to talk about gyroscopic precession. Okay, so let's look at that part, the gyroscopic precession part. So we have a system here. So we can certainly write, so I'm going to ignore the uh, wobbles, because the wobbles don't contribute to the angular momentum very much at all. They barely contribute anything. So let's go back to the Newton's second law, torque, which is dl by dt. And that means it's L1 dot plus L2 dot plus L3 dot. So these two terms are 0 for the reasons stated, because the wobbles don't contribute much to the angular momentum. And then you just have L3, okay, L3 dot. And that is going to be equal to I3 times omega 3. Well, I can write that I3 times omega 3 in vector form as follows. Because the omega 3, which is now called omega naught, since it doesn't change with time, is pointing along the E3 axis. So that's how you would write it in vector form, and you differentiate this. Once again, you have the opportunity now to introduce changes in lambda 3. If pieces are flying off, they're not, so that you just differentiate E3. Now, L3 is the external torque is just R cross mg. So let's write that. R cross mg is going to be lambda 3 omega naught. And the only thing that possibly changes with time is E3. Because of precession, the E3 axis, which is tied to the top, keeps changing with time. Okay, so now I can write this vectorially. This is going to be R in the E3 direction, because R vector is along the E3 direction, cross mg. But the g vector is in the negative z direction of the s prime frame. So I'm going to write this as negative z prime. And that is going to be lambda 3 omega naught E3 dot. So we'll take magnitudes of both sides. If I take magnitudes of both sides, then the magnitude of E3 dot, which I'm going to define as the quantity called omega precession. The rate of change of the E3 axis is called the precessional angular velocity. And the magnitude of this side is just going to be mg times r times sine theta, the angle between r and mg. This angle theta here, which is also, by the way, the same as this angle theta. Divided by, because I'm solving for E3, I'm going to divide by lambda 3 times omega naught. This is your extremely celebrated formula for the precession angular velocity of a gyroscope. You observe at once that it answers to the phenomena we saw during the demonstration part of the video, in the early part of the video, and that is, as these omega naught is not truly constant in that example due to viscous friction. So as the gyroscope slows down, the precessional speed increases. So as omega naught decreases, lambda p increases. So we make that observation immediately. Even though omega naught is not allowed to increase or decrease, it's allowed to do that in a quasi-static manner. So if omega naught decreases, then omega p increases. So we are able to make that deduction out of this system. So for the last part of our video, we're going to have a completely different situation where you have an asteroid hitting the Earth and causing some sort of a disturbance in the wobble. And we're going to see, as a result of the disturbance, how much the North Pole would have wandered in 65 million years. So I'll just make a note that this is the precession angular velocity. So the last part is a fun part because we have to make a ton of assumptions about um, the object that caused the dinosaurs to go extinct. So I read somewhere that it was a asteroid about the size of Mount Everest that came and fell in a crater in off the coast of Mexico, I believe, uh, called the Chicxulub crater. So we have to make some assumptions about what a mountain looks like. I'm going to assume it's a cone. Now, a mountain like Mount Everest is usually, um, Mount Everest, everybody knows, is about 10 kilometers tall. And the base is usually about, there's a bad drawing because the base is usually 3 times as much as a height for a typical Himalayan peak. I don't remember where I read it or if I read it or I'm just making it up, but anyhow, that's my assumption. If that is my assumption, then the volume of the mountain can be, I'll call the volume of the asteroid, VAST, can be estimated. The volume is just 1/3 pi r squared times h, where r is the radius of the base. So that's going to be 1/3 pi, that's 15 kilometers. And the height is 10 kilometers. Well, 1/3 and pi are natural enemies. Here, this is an estimate. It's not a super detailed calculation. So 1.5 squared is 2.25, which I'm going to write as 2. And then I have a 10 to the 4, because that's 1.5 squared, 10 to the 4 here, and a 10 to the 4 there. But that 10 to the 4 is squared, so that's 10 to the 8 times 10 to the 4, so that's going to be 10 to the 12 cubic meters. So volume of the asteroid is 2 trillion cubic meters. Pretty big deal. So the mass of the asteroid, MAST, is going to be the density times volume. Now, most asteroids are about the density of Earth. So it's about the density of Earth times the volume of the asteroid. Well, the density of the Earth I know to be something like 5.5. I'll just call it 5 grams per centimeter cube. But if you want to write it in kg per meter cube, you're going to write it as 5,000 kg per cubic meter. The asteroid volume is up there, 2 times 10 to the 12. So miraculously, it all works out because 5 times 2 is 10. And so that's going to be 10 times 3 times 10 to the 3, which is 10 to the 4, plus 12, 10 to the 16. I remember reading somewhere that the estimate is 15 trillion tons for the asteroid that killed the dinosaurs. And 15 trillion tons is 15 times 10 to the 12 times 10 to the 3. That's metric tons. So 10 to the 3 kg, which is very close to that estimate. So we are good. Now, one big assumption I'm going to make is that the impact was radial. This is not always true. The impact in any disaster movie that you see, it goes through the atmosphere at a steep angle, and then it plows through different cities. It goes over several cities before finally hitting the ocean in a standard impact movie. What I'm going to do, when I say standard impact movie, I'm thinking of this movie called Deep Impact, a Hollywood movie. But what I'm going to assume here is that the mountain pretty much came radially and wedged itself into the earth like a dart. So when you do that, then you lose all the torques. That's the beauty of that assumption. So radial impact means there's no torque. I don't want to mess with torque. So already you can see that this assumption is an important assumption. So all the gamma i's are 0, which means your wobbles, all the wobbles that you have that were approximate. Remember, the wobbles were approximate because we had to make assumptions about the rate of change of gamma 1 and the rate of gamma 2 being small, or some sort of argument of that nature. Well, all that argument is not necessary, and these wobbles are now exact. So the wobbles are exact, and the Earth is very stable from being hit by the meteor. So don't worry, nothing's going to happen to us. Now, let's draw the picture of the Earth to get some handle on what's going on here. The Earth's axes are E3, E1, and E2. The standard polar coordinate system is going to be used where the point of impact would be that. So I'll draw a little mountain coming in like that and wedging itself from radial infinity. The co-latitude is theta in spherical polar coordinates, and the azimuth angle is the angle phi. Okay, we also are going to make the assumption that the Earth is a symmetric top, which is actually a good assumption. If you didn't know, the Earth is what's called an oblate spheroid. An oblate spheroid is pretty much an object like this. It is squashed so that the principal axes I1 and I2 are equal, first of all, and are bigger than I3. So lambda 1 and lambda 2 are lambda, and lambda 3, well, what's lambda 3 going to be? That's going to be the moment of inertia of the Earth about its axis, plus the asteroid, which can be considered a point mass. So the asteroid's moment of inertia contribution is r squared, where r is this distance. All right. Now, lambda, let me call this r 2, and I'll call this distance r1. So lambda 3 is going to be r2 squared, and then lambda 1 and lambda, this is going to be the moment of inertia of the Earth plus mass asteroid times r1 squared, because these moments of inertia are also going to be affected. So now we have everything set up to use our famous wobble equation. The Earth is going to start wobbling. The Earth is being, peacefully rotating about its axis. One day the dinosaur meteor comes and now it starts to wobble in a very stable fashion. So we're going to use this omega b, and I'm going to divide by omega naught. What is that going to be? Well, that is absolute value of lambda minus lambda 3 divided by lambda. And now I'm going to substitute all these things. So if I substitute lambda minus lambda 3, both of them have got the moment of inertia of the Earth, so that'll cancel out. So I'm going to just get mass asteroid times r1 squared minus r2 squared. In the denominator, I just have lambda, which is that. But if you think about it, the moment of inertia of the Earth is incredibly big compared to that. So I'll omit it and write this approximately as just IE. Because I want to calculate something and I don't want to spend a lot of time calculating it because it's a fun calculation. It's not super exact. So I'm trying to make things easy for me. It can all be done exactly if you're sure about what your theory is. But even today, prominent geologists disagree that the dinosaur impacts actually caused dinosaur extinction. The meteor impact actually caused dinosaur extinction. So this dinosaur extinction is not that big a deal anymore. So we'll look at this. But the pole wandering is real, and we'll find out. So we're going to make the assumption that because the mass of the asteroid is only 10 to the 16 kg, and the mass of the Earth is 6.4 trillion kg. So that's about 10 to the 25 kg. It's a full 9 orders of magnitude more. So that clearly justifies the removal of m ast r1 squared from the denominator. So I have that. What is the moment of inertia of the Earth? I've given you the mass, so I guess you can figure it out. But I'm going to use the model that geologists use. The Earth is not a solid sphere. It has actually got several layers. If you remember your high school geography, it's got this inner core, the outer core, the mantle, and the crust. And some of these layers are actually liquid. So the moment of inertia of the Earth can actually be approximated to a very good degree by the formula 1/3 m of the Earth times r of the Earth squared. So the 2/5, not a big deal. 2/5 is 0.4 and 1/3 is 0.33. So the difference is very small. It's not a big deal at all. But I took the opportunity of telling you what geologists think. So omega b over the wobble frequency over the Earth's nominal rotational frequency is going to be m ast divided by 1/3 MERE squared. Now R1 is, looking at this triangle, R1 is RE cosine theta because it's the adjacent side of this triangle. And R2, let me draw another theta that'll convince you of that. So R1 is the adjacent side of this triangle and R2 is the opposite side. So that's going to be RE squared cos squared theta minus sine squared theta. Well, I remember an old trigonometric identity my high school teacher taught me, and that is cos squared minus sine squared is cosine 2 theta. So everything's coming together nicely. The mass of the asteroid I can stick in there. It's 10 to the 16 kg over, observe that the radius of the Earth need not be known in this calculation. Amazing. Doesn't matter how big the Earth is. So that's 1/3 mass of the Earth, which I wrote somewhere there. So that is, I'll write it as 6 times 10 to the 24 kg. It's actually 6.4. And then cosine 2 theta. Okay, the Texas latitude is approximately where the Chicxulub crater is. So Texas latitude is about 30 degrees north, I believe. So theta equals 60 degrees because it's a co-latitude. Okay. All right. Now we'll put these values in there. 2 times 62 is 120, so cosine will turn out to be negative. Better keep that absolute value sign there. So I'm going to get omega b over omega naught is 1/3, and 6 gives me 2. Cosine of 60 degrees is half, so that's going to be 1/4 because there's a 2 downstairs and that produces a half, so that's going to be 1/4 times omega naught. Omega naught is here. 1/4 times 10 to the minus 8, because 16 over 24, 10 to the 16 over 10 to the 24 is 10 to the minus 8. So finally, we have our formula for omega b. Omega b is omega naught over 4 times 10 to the minus 8. So the pole wandering tells you how far the pole has moved. So the North Pole, let's just focus on the North Pole. North Pole wanders in this time, delta north is going to be the radius of the Earth times omega b times delta t, where delta t is a duration since the impact. Now this is of course an estimate. It tells you that the North Pole is pretty much free to move. That's not always true. So let's try to write down what this estimate works out to be. Delta n works out to be the following. The times omega naught. No, that omega naught is over there. So this gives me omega naught over 4. So first let me write down R sub E, that is 6.4 times 10 to the 6 meters. Then let me write down omega B, which is omega 1/4 times omega naught, and omega naught is 2 pi radians divided by 86,400 seconds, which is the duration of 1 day, times 10 to the minus 8 from there, times the duration since the impact of that asteroid. So that's 65 million years. 65 times 10 to the 6 million, and then years is so let me just write a year as approximately 10 to the if I remember right, an year is 3.3, approximately 3 times 10 to the 7 seconds. That's how I roughly remember it. It's about 30 million seconds. Okay, so when you work this out, and I won't do that here, you're going to get 75 times 10 to the 7 meters. Now that's a huge amount. The North Pole cannot have wandered that much. So this clearly tells us that if the North Pole is really free to move, it would have gone around the Earth a few times, is what this calculation is telling us. Now, I don't know if a geologist is going to buy this theory that's come out of this, or they'll just think it's a fun calculation and dismiss it. I'm not sure, but I for one, have not seen this calculation done anywhere, so I thought it was a fun thing to do here.